Hi, my name is Alex Lopez, and this is my lab report for Physics 2211 Lab 2. The purpose of this lab is to analyze the motion of a falling object and to apply Newton's second law to see how the object is affected by the forces of gravity and drag. So the main physics principle behind this lab is Newton's second law, which is shown up top, that the net force is equal to the mass times the acceleration, which can also be expressed as the momentum principle, which is that the change in momentum over time is also equal to the net force. And the big thing with this experiment is that there are two different forces acting on the falling object: the force of gravity, which pulls downward or in the negative y direction, and the drag force, which opposes gravity, so it works in the upward positive y direction. And then the net force is going to be the sum of those two force vectors. And then we have the velocity update and position update formulas. So the velocity update is that the final velocity is equal to initial velocity plus net force over the mass times the time. And then the position update is the final position is equal to the initial position plus average velocity times time. And those both will be used in the computational model. So shown here is the tracker video analyzing the motion of the frisbee as it falls to the ground. So here is the first part of the code that was used to find the computational models, both with and without drag. The only difference is the b at the bottom, which I'll get to in a second. But so you can see the mass is set to 0.175 because according to Google, the average mass of a frisbee is about 175 grams or 0.175 kilograms. And then both the position and velocity vectors are set to 0 to start because the frisbee starts with 0 initial velocity and its position is the origin. And then time is at 0. And delta t is 0.0333 because the video was filmed in 30 frames per second. Gravity is, of course, 9.8 meters per second squared. You have the unit vector, and then b is the coefficient for air resistance. So in the one without drag, it's 0 because we're not taking into account air resistance. And then the one with drag, it's 0.06 because that was what I found to be the most accurate number for that. Here's the rest of the code. This part was the same for both models. So we have while t is less than 0.4667 because that was the total time that it took the frisbee to fall. And then we have the two forces, the force of gravity and the force of drag. So for the force of gravity, it's just negative mass times g in the y direction. And then for the force of drag, it's the b, which was the air resistance coefficient, times the magnitude of the velocity squared, which is going to work in the positive y direction. So then for the net force, we just combine the force of gravity and the force of drag. And then for the velocity, it's the initial velocity plus the net force divided by the mass times delta t. And the position is the initial position plus the velocity times delta t. And both of those are from the formulas shown earlier, the velocity update and position update formulas. Here are the results. You can see the three data sets plotted together. The observed data is the blue line, the computational model without drag is the orange line, and the computational model with drag is the gray line. So you can see the observed data is a lot closer to the computational model with drag, and the computational model without the drag predicted the frisbee falling a lot faster because it did not take into account the air resistance, which opposes the force of gravity, and thus slowed down the frisbee as it fell. So to answer some final questions, which model predicts a terminal velocity and what does it mean for the force when terminal velocity has been reached? So the model with drag predicts a terminal velocity because in that model, the rate at which the velocity is increasing is slowing down over time, meaning the velocity is approaching a constant velocity, which is that terminal velocity. And at that point, the net force acting on the object is 0 because there's no acceleration on it, meaning that the force of gravity and force of drag have canceled out. And then if the object was thrown downward, would the terminal velocity be the same or different from the case where the same object was dropped from rest? Yes, the velocity would be the same because even though it started with an initial downward velocity, it will still reach that same terminal velocity over time. And then some possible sources of error in this lab were the mass of the frisbee was definitely not exact, so that may have caused some errors in the calculations. And then the tracker video is also a little bit off at times, so that may have not been exact.